An incredibly powerful tool in AI and machine learning and data science in whole is a technique called principal component analysis, or PCA. And it is a tool that allows us to take many variables and dimensionally reduce them to some smaller, more comprehensible dimension. So imagine that you have a bunch of data, and for instance, we may have 100 health variable measurements on millions of patients. And so the fact that you have 100 variables like blood pressure, heart rate, etc., we want to kind of understand the relationship among those variables. And more specifically, we want to see what are the most important relationships in those 100. Well, one thing that we could, of course, do is we could pick every pair of variables and look at a scatter plot of that data. But can you imagine taking every pair, which would be 100 combination 2 different ways of selecting two variables from 100 data points, and trust me, that's a large number, and looking at it that way. And then the difficulty that, of course, we'll have is picking apart all of those relationships and expressing them meaningfully. So by the way, 100 combination 2 is the number of ways to select two variables from 100 where the order in which they're selected is not important. There are 4,950 pairs of variables that you would need to consider, and that's impractical, right? And at the same time, it's impractical to take all 100 variables and look at those relationships. For one, we can't visualize in 100 dimensions. Okay, so let's reduce this down a little bit. Let's just say that for our toy data here, we'll have 10 patients, and we're going to measure their blood pressure, cholesterol, BMI, and blood sugar. So let's just start off by taking as our X variable blood sugar and BMI as our Y variable. Okay, so we're going to just consider two variables, and we're going to play around with this toy data just so that we can see how this analysis of PCA plays out. Okay, so here is the data, right? And what we're looking at in this graph is we are looking at BMI on the y-axis versus blood sugar. So what's the first thing that we notice? Well, it kind of seems like increasing blood sugar tends to correlate with increases in BMI. In fact, you could say that as your blood sugar goes up, your BMI tends to go up. That doesn't mean like right now, if you consume a bag of sugar, your BMI is going to suddenly jump. It just means that people who have these measurements of average blood sugars tend to have higher BMIs, or a body mass index. By the way, if you're not familiar with these variables, blood sugar is like the number of milligrams of sugar you have in each deciliter of blood. So it's kind of a concentration. And then your BMI, your body mass index, is a metric that's been used for a really long time. Some people say it's outdated, measuring how many kilograms of mass you have for every square meter of area, so to speak. Okay, and so how do we begin to analyze this data? Okay, well, we see the relationship, and I just want to point out how this technique works, and that the technique is going to show us kind of the same result. So vectors are often, as we've seen, represented with the tail at the origin. So usually, we'd have vectors kind of emerging out of here, right? And so it would make sense to have our data recentered about the origin. So the way in which we do this is for each of our X values, we subtract away the mean. Okay, so for all intents and purposes, if the mean of your data, let's say, rests right there, so that represents the average X and it represents the average Y in our data, right? So imagine that that's the mean right now, and we subtract away all the points from their mean. So we're just getting how far they deviate away from the mean. We get the deviations. So if we subtract away the X mean and the Y mean, imagine that our data looks like this. So we have all N of our observations. So in our case, we would have all of the blood sugar for our 1 to 10 patients, and then we'd have the corresponding BMI for each of those 10 patients. Of course, you want to make sure you pair. This is patient 1's blood sugar, patient 1's BMI. Now, to do this without having to subtract away the mean individually, it'd be helpful to have like a mean matrix. So imagine that what we construct is what we'll call the X bar matrix, which will just contain the same number in each column, or the same number in each row of the same column. And so X bar will be all the way down and Y bar will be all the way down, so that when we take X minus X bar, these matrices, notice what it's going to do. It's going to subtract away X1 minus X bar. And then it's going to subtract X2 minus X bar, and so on until you get down to xn minus x bar. And similarly for the y values, it'll do y1 minus y bar and y2 minus y bar all the way down to yn minus y bar. And so what that does geometrically, if you do that, is it takes your data and it shifts the whole cluster down to the origin. So remember how I said there's like some mean in here? Well, now the mean of this new data is 0. And you can test it out, you can compute it, because you've shifted everything to be relative to the centroid, sometimes called the centroid, or the mean of the data points. So now that we're working with this cluster, now we can sort of think about the vector that represents this. So if I were to ask you, in which direction is there the greatest amount of variability? Okay, so the greatest amount of spread. You would probably say something like that, right? The data really spread very far, for example, this way, right? It actually only goes out just a little bit in each direction, but you can see that along this line, the variability in that data is pretty big, okay? And so my question that I want to answer is, well, let me skip down here. We would like to know in which direction is there maximal variance. In other words, in which direction does the data spread out the most? Now, this will help us explain the relationship between the variables. So the first thing is we need to determine the spread of the data. And so one way to determine the spread of the data is the variance and the covariance. And so we build what's called the variance covariance matrix. So in the top left, if you think about what this is the variance of blood sugar. This will be the variance of your BMI. So along the diagonal, you'll have the variances. And then these two values here, by the way, they're the same. They're going to be the same, because it doesn't matter whether you consider the covariance between blood sugar and BMI or the covariance between BMI and blood sugar, you're still comparing the same two variables. So this will be the covariance between blood sugar and BMI. So it will tell us to what extent they vary together. To know again in which direction there is maximal variance. So eigenvalues and eigenvectors actually tell us where the data points. In this case, the data that we're referring to is the variances and covariances. So let's go ahead and compute this, and we'll come back to sort of the logic of how this works. But notice what we've done again. We've taken our raw data, we've packed it into columns. This would work for more variables and more patients, by the way. You just have to have more mean columns if you had more variables, and a longer mean column if you had more patients. So we took our data, we subtracted the mean matrix away from it, so we basically shifted the data. We're going to call that new matrix, we're going to call that X sub C for X centered, or X centered, and that centers around the origin. And so now to compute the variance covariance matrix, we're not going to unpack this, though you could. It will be, notice that it's 1 over n minus 1, which is the sample variance, and then it's going to be the transpose between xc times xc. Again, what this will produce is it will calculate the variances and the covariances. You can kind of put that together and see how that works if you want. So we would like to know in which direction is there maximal variance, all right? So eigenvalues and eigenvectors will help us with this. So by the way, here is the mean. This is the mean blood sugar and the mean BMI. So we could say that on average, a person has, in this data set, has 120.71 milligrams per deciliter of sugar, and sugar per deciliter of blood. and a body mass index of 25.17 kilograms per meter squared. Here we go. Okay, so notice again, as I mentioned, this is the covariance between, I guess technically, between blood sugar and BMI, and this would technically be the covariance between BMI and blood sugar, and notice we get the same answer. This value, so interpreting the covariance is kind of tough to do, right? Because, well, it just is a measurement of to what extent they vary together, and the units are kind of mixed up. But here we have the variance of the blood sugar, because that's our first column, and our second column corresponds to the variance of the BMI. Okay, so we could say, by the way, the units of these would be square units. So if you square rooted them, you could actually say that the standard deviation. So the variance of blood sugar is 90.54, and this would be units of blood sugar squared. So blood sugar is measured in milligrams per deciliter. This would be squared units, but if you square rooted this, you'd get about what? Just under 10, between 9 and 10, let's say 9.5 milligrams per deciliter. That's how much on average people are spread out around the mean blood sugar of 120.71. Similarly, here you would have units of this is kilograms per meter squared, and it would be square units. So again, if you square rooted that, you get about 2.4 or something like that. Again, that's the average amount by which people's BMI varies about that mean. So here are the eigenvalues. Notice that the dominant eigenvalue is much larger than the non-dominant of 4.4. So that tells us, and we'll come back to this, but the dominant eigenvalue, its eigenvector explains the direction of greatest variance. Okay, so what this means is if I take that vector negative 0.99 and negative 0.14, and I were to plot that vector, that would mean that if I moved over approximately 1 unit to the left, and okay, there's 0.14 is about there, we'll say, so the vector would point in that direction. Now, by the way, that's just the vector, but vector represents a whole line of possible vectors, because remember, any multiple of an eigenvector is itself an eigenvector. So if I plot that line, how would I plot that line? Well, this is the change in y, and this is the change in x. So if I plot this as change in y over change in x, that will give me slope, negative 0.14 over negative 0.99. That'll give me the slope of that vector. And if I plot that, and again, the negatives cancel out, so 0.14 over 0.99 will do just fine. So if I plot that line and I superimpose it over my data, check it out. That is the direction of maximal variance. So if I were to project each of these dots onto this line, that is precisely what we are doing here. We're projecting these points along this line, and notice that the data spreads in that direction maximally from where I've put the brackets, right? So all of the data lies between about here and about here. So how would I interpret this? Okay, well, I could say that the maximal variance is in the direction of the vector 0.14, 0.99. I avoided the negatives, right, because it's the same thing as 0.14, 0.99. This gives us kind of a recipe. It's like a baking recipe. It says that, for every deciliter of blood sugar that you have to add 0.99 kilograms per meter squared of BMI. So indeed, as the blood sugar increases by this amount, BMI goes up by almost 1 unit. So this is just an average of how people's average blood sugar affects their BMI based on this toy data. This is not real data, but probably expect to see something similar to this in real life. Now you notice that there's also another eigenvector. What does that mean? Well, that variance is a lot smaller. By the way, we would say kind of this is like the variance explained. We'll come back to this. But if we look at this other direction, which is kind of almost like the flip in essence, but for every 0.14 units of change in x, there's a negative 0.99 change in y. So for every 0.14, negative point, so it would look kind of like this. If I plotted that vector, it would look like this. And that, notice, that has a much smaller variance in that direction, but that is the second direction of most variance. So if we had 10 eigenvectors for a problem, in descending order of the magnitude of their eigenvalues, it would tell us the direction of change. Now, if I just look at the 92.2 relative to the total, which would be around 96.6, then notice that this is, I don't want to say exactly 100%, but it approaches, well, let me give you an actual measurement. 92.2 out of the sum of the eigenvalues, this is about 95.4% of the explained variance is given by this direction right here. So that's pretty cool. And again, this just gives me a recipe. So now imagine that we're in higher dimensions, like 10 dimensions. And I repeat this process, but I get 10 eigenvalues and 10 eigenvectors. I order them in descending order. I look at the largest eigenvalue, and I can interpret the eigenvector as a corresponding change in all 10 components. We'll look at something a little bit bigger later. You also want to kind of look at similarly sized eigenvalues. So if this eigenvalue were like 80, then it also serves as pretty great importance, right? In that case, they would almost take 50% of the variance each. So, but explaining 95.4% of the variance as taking place in this direction is pretty solid and is pretty much strong enough. All right, so in the next video, we'll kind of unpack what's going on here and look at some larger examples. But again, we could take data that's in many, many dimensions, and we can explain relationships by just looking at the eigenvectors.